Okay, this is our second video on related rates, and we're moving on to problem number 9. So in the last video we ended with problem 8, which was our first application, and we went through some steps like draw a picture, label it, create an equation. Well, before that step was identify your knowns and your unknowns, create an equation, differentiate it, and then plug in the numbers and solve. So we're going to try to do that process on this one as well. And it's talking about a sphere, so we can definitely start by sketching a sphere. But I think in this problem, the sketch itself is not going to be super helpful. So we have a sphere with a certain radius. I'll label that R. Find the surface area of a sphere at the instant when the rate of increase of the volume of the sphere is 9 times the rate of increase of the radius. So this problem is a little bit confusing because we're finding the surface area. And by the way, we should know that the surface area of a sphere is 4 pi r squared. This is one of the most difficult parts of this unit, is remembering all your formulas from geometry. Now we're finding the surface area at the instant when the rate of increase of the volume of the sphere, so we also need the volume formula, which is 4/3 pi r cubed. That's one of those equations that we used in part A, the original video, or the first video. The rate of increase of the volume of the sphere is 9 times the rate of increase of the radius. So the rate of increase of the volume would be described as dV dt, and it is 9 times the rate of increase of the radius, so 9 dr dt. So we're finding the surface area at that instant. Okay, well here's the thing. This equation that we want to work with to get our final answer is kind of like our primary equation, but this other equation is going to help us along. That's like our secondary equation. So a lot of these problems have two equations, a primary equation and a secondary equation. You could debate in this particular problem which one's primary, which one's secondary, really doesn't matter. The point is that we're going to use the volume equation to help us to ultimately get to our answer. There's really nothing else we need to do with our sketch or labeling. So notice that we have an equation that relates the rates of the volume and the radius. Let's go back to our volume equation and differentiate it, and we'll have another equation that relates the rates. So dV dt equals 4/3 pi, the constant, times 3r squared dr dt, the derivative of r cubed. Okay. Now, we can simplify that a little bit. So dV dt equals, we'll cancel the 3's. So we get dV dt equals 4 pi r squared dr dt. Notice we have dV dt equals one thing and dV dt equals another thing. Let's set those equal to each other. So 9 dr dt equals 4 pi r squared dr dt. We can divide both sides by dr dt, and this gives us an equation we can solve for r. 9 equals 4 pi r squared. Divide both sides by 4 pi. 9 over 4 pi equals r squared. And remember, we're finding the surface area at this particular moment. So let's take that, plug it into our surface area equation for r squared. So the surface area is 4 pi times r squared. So the surface area is 9. At the moment when the rate of change of the volume is 9 times the rate of change of the radius, the surface area is 9. And we weren't given any units, so we'll just have to leave it at that. So that one was a little bit less conventional because it involved both volume and surface area, and the answer, the final answer, wasn't even a rate. But you guys need to see a variety of problems. Here is a classic. You have a conical tank. A water tank is in the shape of an inverted cone. Inverted meaning the point is at the bottom. The height of the cone is 10 meters, and the diameter of the base is 8 meters. Now usually when we're working with a cone, we want the radius instead of the diameter, so I'm just going to take that diameter, cut it in half. the radius is 4 meters. The height, pretend that was straight, is 10 meters. Water is being pumped into the tank at the rate of 2 cubic meters per minute. So at some point in time, we have all this water in here. And the rate of change in cubic meters per minute, focus on cubic meters, that's an indication that we're talking about volume. So one of our knowns is that dV dt, the rate of change of the volume, is 2 cubic meters per minute. Is it positive or negative? Is the volume increasing or decreasing? The volume's increasing, so it's a positive rate. So here's the question. How fast is the water level rising when the water is 5 meters deep? Okay, we need a variable that represents the water level. So at any particular moment, let's say the water's this deep, we'll call this R the radius of the circular top of the water, and we'll call this H the height of the water at that particular time. So we are looking for dH dt when H equals 5 meters. So we need an equation that relates the volume to the height, and then we can differentiate it and relate the rate of change of the volume to the rate of change of the height. And if you remember from the first video, we worked with this formula quite a bit. We had the volume of a cone is 1/3 pi r squared h. Now, is r a constant in this problem? No. As the water level goes up, the radius grows. Is h a constant in this problem? No. As the water level goes up, h grows as well. So we could choose to leave both r and h in our equation and differentiate using the product rule, or we can find a relationship between the radius and the height and eliminate a variable. Now I'm going to go with that second plan. So looking at the figure, I'm going to take a bit of it out. We have 4 and 10 as the ratio of radius to height, and we have a similar triangle with r and h as the ratio of radius to height. So because these triangles are similar, we can write a proportion. 4/10 equals r over h. Now I'm going to use that equation to either eliminate r from my volume equation or eliminate h from my volume equation. So I need to think about this. Which one do I want to keep, and which one is it okay to eliminate? So remember, the goal is to find dH dt. So I want to keep h. So I can eliminate r. So going to this proportion here, we can write it as, if I cross multiply, I get 4h equals 10r. Divide both sides by 10, and we get 2/5 h equals r. So we can use that to get rid of r in our equation. So back to that equation, volume equals 1/3 pi times 2/5 h quantity squared times h. And when we square that and we multiply our constants together, we have 4 pi over 75 times h cubed. So now we're ready to differentiate. dV dt equals 4 pi over 75 times 3h squared dH dt. Now we know that dV dt is 2. We'll plug that in. We're looking for dH dt when h is 5. We'll plug that in. So we have 2 equals 4 pi over 75 times 3 times 5 squared times dH dt. Simplifying that, we have 2 equals, now let's see here, 25 times 3 is 75. Sorry about those horrible noises. The bells are ringing here at school. Okay, so we have 75 here, we have 75 here. Cancel those. Now we're going to divide both sides by 4 pi. So we end up with dH dt is 2 over 4 pi, reduce, and it's 1 over 2 pi. That is a positive, and the water level is going up, so that's appropriate. And then what about the units? So H is in meters, time is in minutes, so the units would be meters per minute. dH dt is 1 over 2 pi meters per minute. Okay, let's review the steps that we went through. Draw a picture. It was partially already there, but we also drew another little picture and we labeled our picture. Write down what we know and what we want to find. Find an equation that relates those quantities. We also used a secondary equation to eliminate a variable. Then we differentiated the equation, we substituted in the numbers that we had, and we solved for the one that we were looking for. Those are your steps. Okay, let's keep going. Here's number 11. A light on the ground 100 feet from a building is shining on a 6-foot tall man walking away from the streetlight toward the building at the rate of 4 feet per second. How fast is his shadow on the building shrinking when he is 40 feet from the building? Pause the video, sketch the figure, and then resume, and let's see if we agree on the sketch. So I'm going to go ahead and pause and sketch. You pause too, and then when you come back, we'll see if we agree. Okay, so here's what I have so far. We have the light shining. This right over here. We have the man, he's 6 feet tall. We have the building. And then because of the way the light is shining, it creates the shadow. So this is the height of the shadow. I've labeled it Y. We know the distance from the light to the building is 100 feet. And we know that his distance from the building is changing. His distance from the light is changing. So we're going to label one of those, probably X. Let's say this one here is X. You could use the other one as X, doesn't matter. And so then this here would be 100 minus X. Assuming the building is perpendicular to the ground, I'm going to put a little right triangle in there, and same thing with the man on the ground, a little right triangle in there. Now, what else do we know? He is walking towards the building at a rate of 4 feet per second. So the distance X is growing. So the distance he's walking away from the light is positive 4 feet per second. So I'll call that dx dt equals 4. What do we want to find? How fast is his shadow shrinking? So we want to find dy dt, that would be the rate of change of the shadow at the moment when he is 40 feet from the building. So that means that x would be 60, so that 100 minus x is 40. Okay, so we need a relationship between x and y. Well, this is not a Pythagorean theorem situation because we're not involving the hypotenuse, but if you recall from the previous problem, we do have a similar triangle situation here. So we have this triangle, and we have this triangle, and they're similar. So we can come up with a proportion that relates the corresponding sides. So we have x, the base, over 6, the height, equals 100, the base, over y, the height. Okay, so that's our equation that relates x and y. Now, if you want to, you can rearrange it in all kinds of different ways. And I think because ultimately we're looking for dy dt, I'm going to rearrange it and isolate y. So if we cross multiply, we have xy equals 600. You know, I'm just going to leave it like that. And I'm going to differentiate it now. So using the product rule, we have the first times the derivative of the second plus the second times the derivative of the first. Whoa, I almost put 1. That was crazy. The derivative of x is dx dt, not 1. What was I thinking? Equals 0, the derivative of 600. Okay, so do we have everything we need to solve for dy dt? Well, we do have dx dt, and it's supposed to be happening when x equals 60, but we need to know why. So let's figure this out. So we can go back to our proportion, and we can put 60 in there for x and solve for y. Could have done it right here as well. 60 y equals 600, y equals 10. Okay, so let's put 10 in for y into our related rates equation. So we have 60 times dy dt, don't really need those parentheses, I don't know why I wrote them, plus 10 times dx dt, which is 4, equals 0. So 60 dy dt equals negative 40. Divide by 60, dy dt equals negative 2/3. Now, why did it turn out negative? Is y getting smaller? Yes, as the man moves closer to the building, the shadow, so the light would hit the man's head in a different place and the shadow would be shorter. So it makes sense that that is negative, and the units would be feet per second. Okay. Hopefully you're starting to kind of get the swing of things. The process itself, draw a picture, label it, come up with the equation, and so on, is the hard part. The calculus is not the hard part in these problems. It's actually coming up with the equations, the secondary equations, and knowing how to relate them. Let's take a look at number 12. This is our last one. A camera on the ground 200 meters away from a hot air balloon records the balloon rising into the sky at a constant rate of 10 meters per second. How fast is the camera's angle of elevation changing when the balloon is 150 meters in the air? So again, pause, draw a sketch, and then resume. Okay, so we have another right triangle. We have the ground, 200 meters between the camera and where the balloon took off, assuming we have a right angle there. And then the balloon is rising, so we don't really know that that's not a constant height, so we'll give it a name like y. And we're interested in the angle of elevation, so I'm going to call that theta. And remember, in calculus, our default is radians instead of degrees. So, is everything labeled? Do we know any more? It's rising at a rate of 10 meters per second, so that would be dy dt is 10. And we want to find d theta dt at the moment when y equals 150. So we need an equation that relates theta and y. So we're going to use trig. The tangent of the angle is y over 200. Tangent theta equals y over 200. Just so you know, you can think of that as 1/200th times y. So 1/200th is just a constant. You don't have to use the quotient rule or anything. Now we're going to differentiate. So we get secant squared theta times d theta dt equals 1/200th times dy dt. We know dy dt is 10, so we can substitute that in. And notice that there's no place in this equation that we have to substitute y equals 150. However, we do need to know theta, so knowing the y equals 150 is going to help us find theta, because if we had 150 and 200 and theta, then we could find the length of the hypotenuse. In fact, here we have a 3, 4, 5 right triangle. Hypotenuse would turn out to be 250. And then to find, actually we don't need theta, we need secant theta, right? To find secant theta, we would take the hypotenuse over the adjacent, which does reduce to 5/4, and then we can square that. So we have 5/4 squared times d theta dt equals 1/200th times 10. So now we can solve for the d theta dt, and that gives us our answer. So we have 25/16 d theta dt equals 1/20th once we reduce the 10 over 200. And then we'll multiply both sides by 16, divide by 25. We can reduce, and we get d theta dt equals 4 over 125, and then our units would be radians per second. Okay, so there's your introduction to related rates. I know that was a lot to watch today, but here's the good news. We're just going to practice these all week. You don't have more instruction on it. So today your assignment is going to be to do numbers 1 through 5 on the related rates worksheet, and then we'll talk about and answer questions tomorrow, of course. And then tomorrow I'll assign you 6 through 10, and after that we're going to do some MyOpen Math. So, whoops. Thanks everybody.